We've learned how elements can become stable by sharing electrons in covalent bonding. Now we're going to look at how electrons can be exchanged from one element to another in order to become stable, and that's called ionic bonding. First of all, let's redefine what ions are. Ions are small particles that have a charge. By small, here's what we mean. They're atom-sized. They might be just atoms, or they might be small clusters of atoms. We've looked at the small clusters of atoms called polyatomic ions as we drew Lewis structures in the last unit. We're going to spend a little more time looking at monatomic or one-atomed ions for a little bit here. Anions, recall, are negatively charged ions. Individual atoms can become anions by gaining an electron or more. Here's an example of what I'm talking about. If I have a chlorine atom and it were to gain one electron, I would have a chloride ion. Cations, recall, are positively charged ions. Well, just like anions can gain electrons to become negatively charged, cations can lose electrons to become positively charged. And here's an example of that. Sodium has one valence electron in its dot notation, and if it loses that dot, if it's transferred out into somewhere else, that sodium is now a positively charged ion. It has the same number of protons that it had before, but now it's missing an electron, so it's positive. The electrons that are gained and lost are the ones that are farthest from the nucleus. These are the valence electrons. And just like we saw with covalent bonding, atoms are most stable when they have the electron configuration of the closest noble gas. Call this chart, this represents how stable an atom is, its ionization energy, how much energy does it take to change it, essentially. And the noble gases were the high points, the spikes on this chart. Let's take a look at sodium just as an example. Here's sodium, it's element number 11. The closest noble gas to sodium is neon, one step back on the periodic table. Well, sodium changes to have that electron configuration, and it lost an electron. It moved from 11 electrons to 10 electrons, and that makes this sodium a 1+ cation. Another example is chlorine. Here's chlorine, element number 17. Argon's element number 18, and that's the closest noble gas. So chlorine is going to take on the structure of argon by gaining one electron. Well, now chlorine still has 17 protons, but it's got 18 electrons, so the chlorine is a 1- ion. So another example, magnesium, element number 12. Closest noble gas is neon, element number 10. It's going to back up 2 steps, and now it's lost 2 electrons to become like neon. So that magnesium is now a 2+ ion. And here's one more example, sulfur. Here's sulfur right here. It's element number 16. Closest noble gas is argon, which is element number 18. So the sulfur moves 2 steps, gains 2 electrons, so that it has 18 electrons. So now that sulfur is a 2- ion. Let's look at what happened to the dot notations of these last 4 elements when they ionized. The sodium started out with 1 dot, and it lost that dot, and ended up with none as an ion. Chlorine started out with 7 dots. It ended up with 8 dots when it gained an electron. Magnesium has 2 dots, and we recall that our magnesium lost 2 dots. Sulfur has 6 dots. It's in column 6, 6 valence electrons. And we recall that when it becomes stable, it gained 2 dots. In all cases, we saw that we either had atoms gain electrons, so they ended up with a full 8, a full octet of valence electrons, and that shows a notation that has 8 dots. Like for sulfur, we saw 8 dots. The atoms that lost electrons, the magnesium and the sodium, ended up with the lower shell actually becoming the valence shell. So these ended up having notations that showed no dots. The example, sodium had 1 dot to start with. When the ion was formed, the sodium ion, it didn't have any dots because it lost that electron. When main group atoms ionize, they tend to gain or lose electrons so that they take on the electron structure of the nearest noble gas to get that stability thing. Now, there's a simple way to predict what kind of ion is going to form if we look at the periodic table. Look at this column number 1 over here. Everything in this column has got 1 dot. The quickest way for it to become stable would be to lose that 1 dot. The closest noble gas is going to be the one that has 1 less electron. So in every case, that's going to become a 1 plus ion. So group 1s always become 1 plus ions. Look at group 2s. Closest noble gas is going to be 2 electrons lower, 2 steps back on the periodic table. Back 1, back another one. So everything in column 2 is going to lose 2 dots to become a 2 plus cation. See a pattern developing? Look at column 3. Remember, we're skipping the transition metals, looking only at representatives. So look at column number 3. 3 dots. The closest noble gas is 1, 2, 3 steps back. So it's going to lose those 3 electrons and become a 3 plus ion. Now let's skip over to the right-hand side of the periodic table and look at the halogens, group number 7. 8 dots would be stable. Remember, 8 dots is stable or no dots is stable. This needs to gain 1 electron to become stable. The closest noble gas is 1 electron farther away, 1 step over to the right. And so that's what they do. And they all become 1 minus ions because they've gained 1 electron. Group 6s need to gain 2 dots. And they'll do that to become 2 minus ions. Group 5s have 5 electrons now. 8 would be stable. 1, 2, 3 steps over, and they're like a noble gas. So that's what they do. They gain 3 electrons and become 3 minus ions. Now group 8s are already stable, so they're not going to do anything. They're not going to ionize. And group 4s, well, they could gain 4 dots or lose 4 dots. Turns out they really don't do either one very often. Group 4s, like carbon and silicon, typically are going to covalently bond. It turns out that 3 electrons is about the most you're going to find moving around in exchanging electrons for ionic bonding. We noticed that the left-hand side of the table tended to make cations, so metals typically become cations, and the right-hand side of the table over here tended to become negatively charged, and so we find nonmetals typically become anions.